Hey everyone, have you ever looked at the world and thought, man, it all just seems so random? Well, what if I told you there's a hidden pattern in all that chaos? That even pure chance has a blueprint we can learn to read? Today, we are diving deep into discrete probability distributions to show you exactly how.
So let's just ask it straight up. How can we find a pattern in something that's supposed to be random? It sounds kind of like a contradiction, right? But here's the secret. Statistics gives us the tools to map it all out. And by the end of this, you'll see that structure for yourself.
All right, first things first. Before we can start drawing our map of randomness, we need to get our toolkit ready. We have to understand a couple of key ideas that are going to let us measure and predict all the possible outcomes.
Okay, tool number one is something called a random variable. We usually just call it X, and honestly, it's simpler than it sounds. It's just a way of sticking a number on a random outcome. So if we flip a coin twice, the number of heads we get could be 0, 1, or 2. That number, 0, 1, or 2, that's our random variable, X. That's it.
Tool number two is the probability distribution. Now, if the random variable gives us our list of possible numerical outcomes, you can think of the probability distribution as the actual map. It's what tells us the chance of each of those numbers happening. It's our guide to the landscape of probability.
Now, for this map to be the real deal, it has to follow three simple but super important rules. Rule 1, you have to be using a numerical random variable X, no categories like red or blue. Rule 2, if you add up the probabilities of every single possible outcome, they have to equal exactly 1. And Rule 3, each individual probability has to be somewhere between 0 and 1. Make sense, right?
And just a quick heads up, today we're talking exclusively about discrete random variables. These are things you can count, like the number of cars that pass your house in an hour. We're not getting into continuous variables, which are things you measure on a scale, like your exact height or weight. For today, it's all about the countable stuff.
All right, that's enough theory for now, don't you think? Let's get our hands dirty and see how this stuff actually works. We're going to take these ideas and apply them to a really simple real-world example.
Let's look at the number of females in 2 births. So our random variable X can be 0, 1, or 2. And this table, this is our probability distribution. It tells us there's a 25% chance of 0 females, a 50% chance of 1, and a 25% chance of 2. And notice, what do 0.25, 0.50, and 0.25 add up to? Exactly 1. It follows the rules.
And if you're a visual person like me, a probability histogram makes this crystal clear. The taller the bar, the higher the probability. You can see in an instant that getting 1 female is the most likely outcome. That bar for 1 is literally twice as tall as the others. It's a great way to see the shape of the data.
Okay, pop quiz time. Have a look at this table. It shows the proportion of unlicensed software in a few different countries. So, my question to you is this a probability distribution? Take a second and think about it.
If you said no, you are absolutely right. This thing breaks 2 of our big rules. First, the variable isn't numerical. Country is a category. That's rule number 1, broken. Second, look at that total. The probabilities add up to 2.09, not 1. So that's rule number 2, broken. This is just a table with some numbers, not a true probability distribution.
Okay, so we know how to build the map and check if it's legit. So what's the next logical step? Well, we want to find the center of our map, the average outcome, what we'd expect to happen. This is also going to help us figure out when a result is truly out of the ordinary.
And the key idea here is called the expected value, or just E. Now don't let the fancy name fool you. It's just another way of saying the mean, or mu, of our probability distribution. It's the average result you'd get if you ran an experiment over and over and over again. So, how do we actually find it? Let's go back to our births example. The calculation is pretty straightforward. You just take each outcome, X, and multiply it by its probability. So 0 times 0.25 is 0, 1 times 0.50 is 0.50, and 2 times 0.25 is also 0.50.
And now for the final step. You just add up that last column. And what do we get? 1.0. So the mean, the expected value, is exactly 1. Now this is really important. It doesn't mean you'll get 1 female every time. It means that over thousands and thousands of 2-birth events, the average would work out to be 1.
So now we know the average, but how do we know when an outcome is genuinely surprising? A really handy shortcut is the range rule of thumb. Basically, it says that anything that's more than 2 standard deviations away from the mean is considered unusual. If it's inside that range, it's pretty normal.
Let's try it out. For our 2 berths example, we'll need the standard deviation, which is just a measure of how spread out the data is. In this case, it's 0.7. So to find our significantly high cutoff, we take the mean, which is 1.0, and add 2 times that standard deviation. That gives us 2.4. Since getting 2 females isn't more than 2.4, we'd say it's not a statistically unusual event.
All right, now for the really fun part. We're going to take everything we just learned and apply it where the stakes are high. We're heading to a casino to use expected value to make a smarter, more informed decision.
So here's the deal. You've got $5 in your pocket. You can put it all on number 7 in roulette, or you can make a pass line bet in craps. Which one is the smarter play? Well, we don't have to guess. We can use expected value to figure it out.
First up, roulette. The win is huge, a net gain of $175. But the chance of that happening is only 1 in 38. The much more likely outcome is you lose your $5. So we do our calculation, and we find the expected value is negative 26 cents. That means every time you make this bet, you can expect to lose 26 cents on average.
Now let's wander over to the craps table. Here, you win or lose $5, and look how much closer the probabilities are. It's almost a 50-50 shot. When we run the numbers here, the expected value comes out to negative 7 cents. So on average, you only lose 7 cents per bet.
So let's put them side by side. The verdict is pretty clear. With roulette, you expect to lose 26 cents. With craps, you expect to lose just 7 cents. So even though roulette dangles that giant prize in front of you, craps is, without a doubt, the statistically smarter bet. In the long run, you'll lose your money much slower.
And there you have it. We've gone from basic ideas all the way to making smarter bets in a casino. This idea of expected value is so powerful because it helps you weigh the risks and rewards in pretty much any situation that involves chance. So my final question for you is, now that you know how this works, where else could you use it to make better decisions in your own life?